Uh, Today, good evening all once again, respected IAPT members, professors, physics teachers, scholars and students. Warm good evening and welcome to the third day of this online lecture series. This lecture series is being organized as part of celebrations of International Year of Quantum Science and Technology. This is the third day and we have two sessions today. The session 1, Professor Anwane sir will be throwing light on Dirac picture of quantum mechanics, and the latter part, Professor Ahluwalia sir will be discussing about one of the application part of quantum mechanics. So first of all, let us have the session of Anwane sir, and let me read the profile of Anwane sir. Dr. Shamkant Anwane sir is the professor and head of the Department of Physics at Sri Shivaji Science College affiliated to RTM Nagpur University. With 29 years of experience in teaching and research in physics, Dr. Anwane sir has made significant contributions to the field. During his doctoral research, he was honored with the prestigious SRF by the CSIR, Government of India. He has completed MRPs and COCs funded from UGC on mathematical modeling using Maple. Dr. Anwane has been nominated to the Board of Maple Ambassadors for the SARC region, where he inspired and educated others about the benefits of Maple in STEM education. Additionally, he is the president of the Sub-RC of IAPT for Vidarbha region and an executive committee member for the Maharashtra state. He is on the board of associate editors of IAPT Bulletin. He has served as a member of board of studies for few autonomous colleges and currently is the member BOS in Applied Science and Humanities for the Faculty of Engineering at RTM Nagpur University. Dr. Anwane has played a pivotal role in organizing numerous national and international conferences and has published around 30 research papers in journals of national and international repute. He has published 2 books with national level publishing house and 4 with international level publishers. To reach a broader audience, he developed 4 courses that are available on Udemy. He made available more than 200 video lectures on YouTube channel on his name, Shamkant Anwane, for a variety of topics for UG and PG level students. Dr. Anwane has also visited several prestigious institutions, including the National University of Singapore, Ajmer Institute of Technology in Turkey, and Stony Brook University in New York, USA. With all these credentials, on behalf of IAPT, I welcome Anwane sir to deliver your lecture. Welcome, sir.
Thank you, sir. Am I audible?
Yes, sir, you are audible. Yes.
I'll share the screen.
You are the co-host, sir. You can share.
Yes. Is it visible?
Yes, sir. Visible.
Right. Thank you. Today, I would first thank for nice introduction, Professor Madhusudan. I am bestowed with a responsibility to portray the picture by Paul Dirac, who actually saw beauty in the physical equations. And he had a very strong belief that his equations are correct. He was criticized. I'll explain the criticism at the end also, so that we can take inspiration from how he was criticized, and after that, there was experimental evidence of antimatter. At the outset, I would like to pay my humble homage to Professor D.P. Khandelwal sir, who started this association of teachers, which has taken a wonderful shape. And I very sincerely feel and many times report to Professor Ahluwalia sir that in this fraternity, I really feel happy than anywhere else. I pay humble homage to Dr. Punjab Rao Deshmukh, who was first agricultural minister and who initiated Shivaji Education Society, and that is running about more than 300 institutions in Maharashtra. And I'm under the umbrella of that Sri Shivaji Education Society, working with Science College in Nagpur. To set the tone of my lecture, I would prefer to read a couple of paragraphs so that I can begin my discussion from the energy equation that comes from special theory of relativity. There was a time when everything happened. Was it a random or a seeming miracle sometimes attributed to the unseen hands of the divine being? Then the Greek and other ancient civilizations began to explore the rationality and logic to explain how the universe works. The paradigm shift came through the likes of Galileo and Newton, through the introduction of classical mechanics. The universe was then built as a kind of cosmic clock, ticking with mathematical precision, where almost every moment and phenomenon could be explained and predicted through observations and equations. In early 20th century, this view of mechanical, deterministic, and predictable universe was shattered with the advent of relativity and quantum mechanics. Time was no longer set in stone, and precise location of a particle was no longer measurable. Einstein, Planck, Bohr, Schrödinger led this new paradigm shift. This might seem like the end of the story, but there has been one additional, more recent paradigm shifting development in physics that perhaps did not receive much fanfare, but it is undoubtedly equally profound. And that is how quantum mechanics was supplemented and made more complete by quantum field theory. It is the basis of the best theory we have in physics today to explain nearly everything, called the Standard Model for particle physics. The two revolutionary theories of early 20th century were quantum mechanics and relativity. Here we are going to investigate how quantum mechanics and special relativity can be combined to give a more complete theory for the electron using elegant operators. This leads us to the Dirac's equation and the equation of relativistic quantum mechanics for electron. The Dirac's equation explicitly requires spin as an intrinsic property of the electron. It gives improved value for hydrogen atom energy levels, including the fine structure, and it predicted the existence of antimatter before there was any reason to imagine such a thing. We only needed we only needed a single equation from relativity that comes from E equal to mc square. So I shall delve into the discussion. Here, we are having different branches, and we are going to talk about combine the spatial relativity and quantum mechanics. We are going to roll through a lot many topics listed here, and I shall begin my discussion with 4 vectors in spatial relativity very quickly, so that the budding students also can understand where from the energy equation comes. I shall be using the concept of 4 vectors. in spatial relativity. To describe an event, we need 3 position coordinates and time coordinate. But the time coordinate has dimensions in second and space coordinates have dimension in meter. So to make it proper, Einstein has given us an idea to consider C into T, and without the loss of generality, we can set C equal to unity and we can consider the space-time continuum. Now the inner product of 4 vector with itself by definition is the first element C square T square minus X square minus Y square minus Z square. So this can be written as R bar also. So in the first equation, the last part you can observe CT comma R, where R bar is a usual vector that we have learned from 11th standard itself. Now, in compact form, we can write the inner product of X with itself as C square T square minus R square, and that is actually the interval in spatial relativity, and this interval remains invariant for all inertial observers. Now, for generalized representation, this event we can represent as x0, x1, x2, x3. And in general, we can write that x suffix mu, where mu can roll from 0, 1, 2, and 3, where 0 corresponds to time representation and 1, 2, 3 corresponds to x, y, z. Similarly, the event coordinates for an observer in inertial frame of reference moving with some uniform velocity, we can have x dash that is equal to ct dash comma x dash y dash z dash, and similarly it can be represented in the notations I have described earlier with a dash that merely reminds us it is for another observer who is in another inertial frame of reference. And that inertial frame of reference by definition is moving with uniform velocity. And x dash inner product with itself also gives us c square t dash square minus r dash square, that is equal to s square, that is interval, and you can observe both the intervals are identical. So can I get a pointer here? Okay. So we can equate both the equations, and to make an argument that comes from the classical theory of fields by Landau and Lipschitz, we are attaching clock to the origin of the inertial frame of reference that is moving with velocity v with respect to stationary observer. In mathematical sense, we can say r dash equal to 0. It means x dash equal to 0, y dash equal to 0, z dash equal to 0. And that is how on left hand side we can have only c square t dash square equal to c square t square minus x square minus y square minus z square. So taking square root on both sides and simplifying, we can obtain the relation ct dash equal to ct into under root 1 minus v square by c square. So v is constant, c is absolute constant, and if we take differentiation on both sides, we can write dt dash equal to dt into under root of 1 minus v square by c square, or else the last equation dt dash by dt equal to under root of 1 minus v square by c square. We shall take reciprocal of this last equation, and on the new slide, I have picked it as dt dash upon dt is equal to 1 upon gamma. A reciprocal we can consider later on. So x we have, and we now want velocity, that is 4 velocity. X is a 4 vector and u is a 4 velocity. that can be obtained by differentiating this event x with respect to t dash. And we can write d dt dash operated on ct x y z. So instead of ordered pair that we have normally, here we have 4 elements. So we can write c into dt by dt dash, and we are employing chain rule to write dx by dt into dt by d dash, and then substitute dt by dt dash as gamma, and we can have 4 velocity. Similarly, can I move this? Similarly, we can have momentum after multiplying m0 to this velocity, so that will lead me to 4 momentum. So I can write in general the 4 elements of momentum are mc, mass into velocity. This is relativistic mass incidentally, which is m0 into gamma, then m into vx, that is x component of momentum, y component of momentum, and z component of momentum. And in the compact representation, we can have ordered pair P0 and P bar, where P0 is mc, that is mass into velocity of light, and Px is relativistic momentum. Now, we are taking inner product of P with itself. By definition, first part square, that is P0 square minus mod of P square, will be the result by definition. So that leads us to M0C whole square. P0, here we are borrowing only one thing, that we already know E equal to MC square. So MC will be E by C. So P bar dot P bar, we are rewriting as P0 square minus mod P square, as P0 is being replaced by E by C square, and mod of P square, simply I'm writing P square, that is equal to M0C whole square. So this is the actual equation that we are going to use in quantum mechanics to write in form of operators. So I'm just rearranging that equation to obtain the desired form. Most of the time in undergraduate level, we are looking at this equation as E square is equal to P square C square plus M0 square C to the power 4. It is the same one. Now, going further, P0 is E by C, and E by C is M0 gamma C. And here we want to represent the denominator under root 1 minus V square by C square as 1 minus V square by C square to the power minus 1 by 2, and we can go for binomial expansion, and we can conclude that the energy of the system is rest energy M0 C square plus kinetic energy. Now, I want to compare these 3 equations. Dirac we are going to deal today, and in last 2 lectures, we have taken the basic leap in quantum mechanics, and yesterday we have discussed that Schrodinger's equation, and Professor Pruthul has touched to Klein-Gordon equation also. So Schrodinger's equation is a non-relativistic equation, whereas Klein-Gordon equation is relativistic one, and the Dirac's equation is relativistic, but the intrinsic spin comes into his equation. That is what we are going to learn in today's lecture. Schrodinger's equation is quantum physics. Klein-Gordon equation is relativistic quantum physics, and Dirac's equation is going to talk about elementary particles, especially fermions, and we are going to talk a special case today about the spin of electron. Schrodinger's equation has offered us many solutions, to quite a level of our expectations, and space, time, and energy momentum unification in Klein-Gordon equation has offered us better advantages, but the results are not very satisfactory. The Dirac's equation has given us the leap into antimatter. Schrodinger's equation is based on Newtonian. Klein-Gordon is obviously relativistic with no spin representation, and Dirac's equation unlashes the spinner's part. Schrodinger's equation has offered us a solution, but it is philosophically unsatisfying to a larger extent. However, the Klein-Gordon equation gives a subtle hint of antimatter, or even it was ignored in the beginning. But Dirac's equation has changed the entire subject to a new regime. Now, the mass shell from relativity that we have just now derived, we shall consider here. And here I am going to write wave function directly as amplitude into exponential of minus I upon h cross et minus p dot r. This I have represented as, again, amplitude into exponential of minus I upon h cross, the 4 momentum inner product with a vector, that is event. So event we have represented like x, p we have represented like this, and p dot x we are taking as EC into CT, that will make ET, and p dot r is simply p dot r. So this is how 4 vectors have helped us. Now, to establish Klein-Gordon equation, we shall use the energy operator, that is IH cross del del T operator. When operated on wave function, eigenvalue will be the energy of the system. And we are interested in E square by C square. So on the right top corner, you can observe the equation. We are trying to resemble things from operator to reach to that equation. So we want E by C whole square. So this energy operator, we are operating on itself. So that is twice representation divided by C square. So I square into I into I will be I square, that is minus 1 h cross square upon C square into second order time derivative. And to obtain momentum, we need minus IH cross partial differentiation with respect to x, then y, and then z. It can be clubbed together with the nebula operator. Now, we are operating momentum again on itself, and we are assigning it a minus sign. So, minus px square, because the resemblance on right-hand side top equation, I want minus p square. So first, minus px square will be h cross square del 2 by del x2. Similarly for y and z component. And minus p square, I'm writing in the violet color as minus px square minus py square minus pz square. That is in fact h cross square Laplacian operator del square. Now we want to plug in that into the mass shell equation that we have just now established using 4 vectors, and minus h cross square by c square del 2 by del t2 plus h cross square Laplacian operator del square, that is equal to m0c whole square. Now, this is what is known as Klein-Gordon equation, one of the forms you can consider, and we can have a D'Alembertian operator to represent 1 by c square del 2 by del t2 minus del square as a D'Alembertian operator. And here we are putting mu. Earlier I was talking about mu as 0, 1, 2, 3. Here it is m0c upon h cross. And if you consider electron, then the value of mu is 2.59 into 10 power 9. Just to give a glimpse, I have estimated this value, and the highlighted bracketed equation is a Klein-Gordon equation we have derived from mass shell that comes from special relativity. And this is the compact version, last equation. Okay, now we shall verify the solution, whether it is working or not. So for that, we have represented 4 momentum and 4 position, and taking inner product P dot X, and we can obtain ET minus P bar dot R bar, that is the usual momentum and position vector. And then we are operating D'Alembert operator on the wave function psi. So here on right top corner, we have 2 equations that are representing the same thing, that is wave function. One first representation is in terms of 4 vectors, and second is an elaborated representation of the same thing. Now D'Alembert operator, we are operating on the wave function. So conveniently here, amplitude I have set to unity so that it should not disturb the differentiation process. In fact, that is a constant that comes from in general complex representation. So D'Alembert operator operated on e to the power I upon h cross p bar dot r bar minus et. And in the second representation, I have expanded the D'Alembert operator as 1 by c square del 2 by del t2 minus del square operated on exponential term. And here we are trying to find out the derivative with respect to time 2 times and with respect to space 2 times, and we obtain something as m0c upon h cross square with minus sign into psi, that is actually minus mu square psi. So we have started with D'Alembert operator operated on wave function, and we have obtained on right hand side as minus mu square psi. So if you take it on left side, it will be plus, and you can say that this equation is satisfied. But even though this equation is satisfied, the things are not too satisfactory when it is applied to hydrogen atom. The success of Schrodinger's equation was also not attained by the Klein-Gordon equation. That is the sad part which has heated the development of the subject. And one more problem, one more technical problem has arrived that I want to elaborate through the discussion of probability density and probability current. So I have written the Klein-Gordon equation for wave function psi, and second equation for its complex conjugate. And to first equation, I'm multiplying by minus psi star on both sides. And to the second equation, I'm multiplying by plus psi on both sides. And I'm adding these 2 equations to obtain something very interesting. That is psi D'Alembert operator psi star minus psi star D'Alembert operator psi equal to 0. So this leads to the expanded version that is appearing on your screen. And we have some equation which has a great resemblance with the continuity equation you can observe. And del t of rho plus divergence of j equal to 0, where you can relate from this continuity equation what is the probability density and what is j. Now probability density, you can look at the equation. Inside bracket we have psi into partial derivative with respect to time of psi star minus psi star into partial derivative with respect to time of psi. So depending on the first part is bigger or second part is bigger, the value of density depends. And we can lead to a situation sometime where the density, probability density can be negative. This was one of the problems, and this has also challenged the Klein-Gordon equation. So whatever I have explained to you, that is represented in the slide. In Schrodinger's equation, the probability density is mod of psi square, and it is always positive, and we did not face any trouble, and we did not know whether this region of trouble is overcome inside Schrodinger's equation or not. But in case of Klein-Gordon equation, there is a dependence on situation whether the probability density can be negative, and that leads to some complication that cannot be explained. Dirac's approach by tapping the beauty of equation. I read somewhere that in one conference, Dirac, Einstein, and all stalwarts of quantum mechanics were present, and he argued there, but nobody paid great attention to what Dirac was saying. And today we are assembled here under the banner of IAPT to understand what was the Dirac's idea and how he tapped the beauty in the equation. I missed one point. In Klein-Gordon equation, we have E square equal to something, and when we want to find E, we are taking square root, and we have a plus sign and minus sign that leads to negative energy, and that was also a trouble that time, but people did not pay much attention to the Klein-Gordon equation because it has already landed into difficulties. Now, the mass shell P dot P, we have already established. We have energy momentum operator, and the first order in space time, we have written those equations. And see what I have done. I have taken on right hand top corner, you see m0 is equal to m. Now rest mass m0, I am dropping the notations of special relativity, because every time writing m0 is, I found difficult. So I have set m0 equal to m, and just to remember that we are talking about the rest mass m0, and I have taken square root of the mass shell equation we have. So on right hand side, we have mc, which is in fact m0c, and we have under root e by c whole square minus px square minus py square minus pz square. And here, the Dirac's idea was, he has represented this under root by a times e plus b times px plus c times py plus d times pz. And now, if you square this equation, what will happen? You are removing the square root, and on right hand side, you have 4 terms and square of that. If you work out that square, you will lead to 16 terms. And to explain this idea, I'm going to consider a fundamental equation. Instead of the equation on left hand side on the left top corner, I'm writing e square minus p square simply, that is equal to m. Here I have set c equal to 1. So my equation is very, very simple. So m is equal to under root of e square minus p square. Now I'm writing under root e square minus p square equal to a into e plus b into p. And whatever I have done in earlier slide, I'm doing the same thing. I'm squaring the equation on both sides. And on left hand side, the square root is removed. We are left with e square minus p square. That is equal to ae plus bp whole square. So x plus y whole square is x square plus y square plus twice xy. So x and y, we have real numbers or something like that. But here, I really do not know what a and b is. What I know is energy and momentum. So those numbers are commutative. E into P equal to P into E is all right. but A into B, I do not know whether it is B into A. So E square minus P square will be AE into AE plus BP operated on BP, because A and B, we do not know, energy and momentum are also operators. So we have to check whether they commute or not. Then AE operated on BP plus BP operated on AE. Now, the first part is all right. The second part is AE multiplied by BP plus BP multiplied by AE. Now here, you can observe that A is operated on B into EP plus B is operated on A into EP. So EP commutes, that is not a problem, but whether A and B should commute or not, that is a great deal. And here, to reach to our equation, what is required? A square should be 1, B square should be minus 1, and AB plus BA should be 0. This was the wonderful idea that Dirac has tapped here. I believe that this is one of the great ideas that has led to some equation, and that equation is so wonderfully working that has led to a new branch, and that is the branch which is the most successful branch of theoretical physics. So A square should be unity, B square should be minus 1, and AB plus BA should be 0. So AB must be equal to minus BA. So these are not simple numbers. 3 into 4 is never equal to minus 3 into 4. So 3 into 4 is equal to 12. 4 into 3 is equal to 12. That should be 12 plus 12, 24. But here we have to hunt out something about A and B. So this is a simpler version. Now let us go to the cryptic version, where we have A, B, C, D, which are appearing in the equation, and we have 16 terms. And in those 16 terms, we have to look for what is happening where. And here, actually, I don't have pointer to show you what I mean to say, but I'll try to narrate you here that we are interested where E square should remain as it is. That the second box on left hand side should be minus P square, the third box should be minus PY square, and the top box should be minus PZ square along the diagonal. Whereas the identical color on right hand side, you can see AB into EPX and BA into EPX. This should eliminate itself. So we want something AB equal to minus BA, sort of, so that it leads to the equation that we were talking about. So AB plus BA should be 0, AC plus CA should be 0, AD plus DA should be 0, BC plus CB should be 0, BD plus DB should be 0, and CD plus DC should be 0. These are the restrictions that we have, and how those will be satisfied, that was, difficult. Dirac opted Pauli's matrices sigma 1, sigma 2, sigma 3, and identity matrix. And here we have 4 such 2 by 2 matrices, and he used them to build a 4 by 4 matrix, like A, which I'm going to shorthand to gamma 0, gamma superscript 0. B, I'm going to represent as gamma superscript 1, and C as gamma 2, D as gamma 3. So the young budding students can take a screenshot of this and actually verify whether this works or not. It is a very delightful experience to see that with this aid, our equations start working precisely. And here on the last equation, I'm writing MC, that is M0C actually, as I said earlier, equal to gamma mu P mu. So gamma 0, gamma 1, gamma 2, gamma 3 are four matrices, and we have four momentum P mu. So one is superscript, another is subscript. So we are in the tensor form, and here we are using the Einstein summation convention. The dummy indices which are repeating over, we have to take summation on that. So this is another compact version of the Dirac's equation you can consider. So here we are representing the same thing in terms of operators. The four momentum I have replaced by IH cross partial differentiation operated with mu. It means that when it is del 0, it means that we are having del t of something. And when mu is equal to 1, then we are having del x. When mu is equal to 2, it is del y, so on and so forth. So we have this expanded version of the same equation, which was written in the compact form, and we need psi to be a column matrix in which we have psi 1 and psi 2, one spinner psi A, and psi 3, psi 4 as psi B, the second spinner. And these are the four wave functions which are clubbed together to represent our wave function in complex form. Psi 1 talks about the electron with spin up. Psi 2 talks about electron with spin down. Psi 3 talks about spin up positron, and spin down positron is being represented by psi 4. Now here I'm calling equations, which is a compact version of the Dirac's equation, expanded version. Then we are having P subscript mu and P superscript mu to represent four momentum. Actually, on left hand side, it should have been capital P. That is my typo mistake. And when you are taking product of two, you can see that P0 into P0, that is E square by C square, then Px into minus Px, that leads to minus Px square, so on and so forth. That is the tensor notation. And in the compact version, we can write gamma 0 square should be unity, gamma 1, gamma 2, gamma 3 squares should be minus 1, and the commutation relation gamma mu plus gamma mu should vanish for all mu different than mu. And these are the four matrices, gamma 0, gamma 1, gamma 2, and the last one should be gamma 3. That is again a typo mistake. And these are basically raised from unity matrix, zero matrix, sigma x, sigma y, sigma z. Those are Pauli matrices, sometime referred in form sigma 1, sigma 2, sigma 3, and sometime in this sigma x, sigma y, sigma z. All right. So again, the previous equation is recalled here, and the Dirac's equation I'm representing for electron at rest. So when we are talking about electron at rest, it means that the space momentum for that should be 0. And P superscript mu, I have written as P0, which is actually E by C, and other elements 0. So I'm applying Dirac's equation for electron at rest actually. And here we have written P mu, and I have recalled the Dirac's equation, and there we have explored gamma 0, P0 is the only appearing term. Gamma 1, gamma 2, gamma 3 have vanished because Px, Py, Pz are 0, minus MC operated on psi equal to 0, and this leads to a final equation gamma 0 psi is equal to MC square upon E psi. You already know that gamma 0 is a 4 by 4 matrix that is multiplied to psi, which is actually a column matrix of 4 elements we have just now seen. So that is appearing on your screen. And on right hand side, we have MC square upon E. So the bispinner is represented by psi 1, psi 2, psi 3, psi 4, and the eigenvalues are plus minus 1. So MC square upon E is equal to plus minus 1 is the solution appearing. And this leads to a situation where psi 1 is equal to psi 2. Sorry, psi 1 is equal to psi 1. See, I don't have again a pointer. Can I have a pointer here to show you equation? I think. Can you see my cursor? So
Yes,
this,
your cursor is visible. You just move your finger on the, and maybe it will start moving on the screen.
okay, sir. So
Control
sir,
plus L actually may activate laser pointer.
control plus
L.
control plus L and try. I think it is not working. Okay. So when we are making the matrix multiplication of this 4 by 4 matrix with this column matrix, 1 into psi 1, 0 into psi 2, 0 into psi 3, and 0 into psi 4, this leads to only psi 1. So this will lead to psi 1, psi 2, minus psi 3, minus psi 4 equal to MC square upon E psi 1, psi 2, psi 3, psi 4. And we are left with psi 1 equal to psi 1 and psi 2 equal to psi 2. There is no trouble in having such equation. It is true for all values of psi 1 and psi 2 that belongs to the complex representation that we can have. And then psi 3 equal to minus psi 3 is not permitted. Psi 4 equal to minus psi 4 is not permitted, and that is only true when psi 3 and psi 4 are 0. So this leads to a situation for psi electron equal to the matrix where we have a coefficient A, B, 0, 0, because 0, 0 has bound to come because psi 3 equal to minus psi 3 is not permitted, and similarly for psi 4. So this leads to the situation of electron, and here we are having similar equations wherein I'm writing the same things for electron, and then I'll extend the idea for positron. So here grad of psi, for momentum operator, we are finding a grad operator is operated on a column matrix psi 1, psi 2, psi 3, psi 4, which is a bispinner. We obtained something, and that is equal to 0. It means that those parameters are constant. So their derivative is 0, means they are constant. So psi is constant in space and has no dependence on position. We have started this discussion for electron not moving. So space is not going to play any role. And for positron, we have the another solution, which was that MC square upon E equal to plus minus 1. So I'm taking that minus part. So psi 1 equal to minus psi 1, which cannot be true except psi 1 equal to 0. Same for psi 2. but psi3 equal to psi3 and psi4 equal to psi4 is possible for all assigned wave functions, and positron can be represented in this fashion. So electron and positron representation can be done in this fashion. Okay. Now, the generalized representation for electron and positron can be using the eigenspinor U1, U2, U3, U4, and then we need to normalize that. And for normalization, we are exploring the trick of taking under root of A star plus B star, so that mod of A square plus mod of B square should be unity, and U1, U2, U3, U4, they are nicely representing electron with spin up. The first case, electron with spin down, and this will be positron with spin up, and U4 will be positron with spin down. Okay, now we are again going back to the basic equations very quickly, and I want to represent something very interesting, wherein we are segregating the basic parts. So here E equal to M0 C square inside bracket 1 minus V square by C square to the power minus 1 by 2. We have made a binomial expansion of that. And what we have done, M0 C square plus the next term we are taking 1 by 2 M0 V square common. And then we are left inside the bracket with 1 plus 3 by 4 V square by C square plus 5 by 8 V to the power 4 by C to the power 4, so on and so forth. And here you can observe that this is the rest energy. First one is the rest energy part. Second one is the kinetic energy part. And the third one is relativistic correction. So this is in steps you can look at how this relativistic quantum mechanics building blocks are working. And when we are talking it for photon, the rest mass is 0. And this is a popular thing, everyone knows E is equal to h nu appears from the same equation, which was Mass-Shell equation. Now slope and curvature. First derivative represents slope, and second derivative represents 1 upon the radius. So that concept we are using, and we are talking about wave function psi, and we are taking time slope and space slope. That is derivative with respect to time and derivative with respect to the space coordinate x, y, z, depending on the situation. And when we are talking about time curvature, that leads to minus omega square, and space curvature, that is second order derivative, we are talking about minus k square, where k is a wave vector kind of representation. And in terms of operators, energy operator is IH cross into slope in time, and momentum operator is minus IH cross into slope in space. So here, that usual equation which we call Hamiltonian, the operator that yields energy we call Hamiltonian operator, and that is IH cross del del T. It is operated on the wave function, and we get energy eigenvalues, and this is the momentum operators, and momentum operators are momentum position and momentum operator is not commuting, and we cannot simultaneously measure those quantities according to that principle, Heisenberg's uncertainty principle. Now, angular momentum representation, I'll very quickly go through that, wherein we are having R bar cross P bar, and we are having components of Lx, Ly, Lz. And here we are talking about the operator form, where operator Lx, Ly do not commute. They rather yield IH cross into Lz. Then quantum spin, we are talking about S is equal to 1/2 ms rolls from minus S to plus S, that leads values of S from minus 1/2 to plus 1/2. And capital S is under root of S into S plus 1 into H cross, that leads to under root of 3/2 H cross. These are the popular things we have learned in the early part of quantum mechanics. And here we are having bracket notations, wherein we are writing the operators in that form, and their normalization, and the generalized representation of those same things with A, B, C, D, and U, V, that has usual representation meanings. And I'm just rolling through the bunch of equations so that I can save time on the subtle part of spin representation in quantum mechanics. And I want to go to the electron spin representation. The spin up part, a spinner can be represented by psi 0, and spin down 0 psi, and the generalized representation in bracket form, in the ket form, psi, and its normalization. And okay, in Klein-Gordon equation, we are having this representation, wherein we have two roots, and we have second order time derivative, and second order differential equation leads to kind of vague things, and that leads to certain problems. And the prior knowledge required for second order equation is more that you should know the wave function, and you should know the first order derivative with respect to time. And the success of hydrogen that was achieved by Schrodinger's was not achieved by Klein-Gordon equation, wherein we have second order time derivative, which is unlike to the one we have in I think I have confused Klein-Gordon. In Klein-Gordon, we have second order time derivative, and in Schrodinger, we are having first order time derivative. So here we have raised our difficulty in Klein-Gordon equation. However, in Dirac's equation, we have simpler terms, wherein we have first order differential equation. All right. Now, this is the Dirac's equation we have, wherein we are representing, instead of gamma, we have representation in terms of alpha x, alpha y, alpha z, and beta. And the constraint on that in another terms. And we have Pauli's matrices satisfying our requirement. And here I want to emphasize on, we are in need of such 4 elements, whereas we have only 3 Pauli's matrices. So to obtain 4 matrices, we have, Dirac has used the Pauli's 3 matrices along with identity matrix to raise the 4x4 matrix, which we have already discussed, that is appearing on your screen. And in the matrix form, the Dirac's equation appears like this. All right. So the last equation appearing on your screen is the Dirac's equation in the matrix form, and psi is a bispinner, and when we represent, we replace that psi by a column matrix, psi1, psi2, psi3, psi4, the equation looks like this big equation appearing on your screen. And after simplifying, after solving the product of the 4x4 matrix with a column matrix, you can obtain this Dirac's equation in this form. Now, the same equation that we have represented for free electron, we can roll through that, and I want to show you the 4 equations can be raised. The last 4 equations appearing on your screen, they are raised out of the matrix equation, first equation appearing, and this is the equation for free electron, and the momentum is 0. So the blue box that will disappear because we are considering electron at rest, and the simplified version is like this. And if you set C equal to unity, we get this solution. I think how much time is left? 7:40. I'll quickly try to conclude. I think I'll have to roll through some slides. So I want to comment that the Hamiltonian and LZ do not commute, whereas J commutes. So that was the interesting part, and with that, we are. I'm just skipping some equations. So here we are considering that the electron is moving, but for not having much complicated equation, we consider that the electron is moving only in x direction. So Py and Pz component is should disappear from our equation. So the red bracketed equation has partial differentiations with respect to y and z that should disappear, and the equation can be simplified to set of 4 equations that are appearing on the left bottom corner, and that leads to the 4 components: psi1, psi2, psi3, and psi4. Now, this very solution, when subjected to finding of A and B from solution, that leads to again mass shell equation like E square equal to Px square plus M square, and by eliminating B again we get the same equation. So we have 2 consistent equations that are for psi2 and psi3, and the moving electron can be represented by this set: psi with spin up, spin down for positron, and electron can be represented like this. So I think I should lead to some conclusion by representing a diagram wherein we have E square equal to P square C square plus M0 square C to the power 4, and that offers us 2 parts, one positive and one negative. So Dirac tried to explain the negative energy states, and he landed into trouble. And I want to explain that trouble to you, and then I'll conclude my discussion. Here we have positive energy levels. When the momentum is 0, E1 is mc square, then E2, E3, E4, we can lead to infinite energy that is permitted because E is equal to mc square, and m is relativistic mass, which is equal to m0 upon under root 1 minus v square by c square. And when we lead to velocity closer and closer to velocity of light, that energy goes on increasing and there is no upper limit. Now consider an electron in energy level E2 that jumps to lower energy level by emitting radiation. And here we have highest negative energy level, which is represented by minus E1 equal to minus mc square, so on and so forth. So as we are going to the ladder, lower and lower ladder, that is increasing and increasing value of momentum. So actually this was leading to trouble when electron is jumping from, say, E2 level to minus E1 level. It should release radiation of frequency. That is the formula is appearing on your screen. And what happens if this goes on happening? We have negative energy levels, and electrons are jumping from positive energy level to negative energy level. It will go on emitting radiation of higher and higher frequency that can lead to trouble. For sustaining life also. So the Dirac's explanation of C of electron, wherein he envisaged that we have negative energy levels and those are fully filled and it is not observable. That was his contention. And when the electron is supplied with energy, it comes into positive energy level. That was his contention. So in 1929,
Anwane sir, sorry to disturb your flow. We have next session.
yes. Yes, sir. I'll conclude in 2-3 minutes only. So Anderson's experiment came to his rescue for the explanation, and the Dirac's C explanation was then replaced by a new idea where a photon disappears, a photon of sufficient energy twice mc square disappears, and an electron and positron pair is created. So I want to highlight few things that in 1929, Dirac submitted work around this problem in his paper entitled The Theory of Electrons and Protons. In the subsection which is appearing on your screen, he titled Solution of Negative Energy Difficulty. After noting the problem, he offered a solution. You can see the lines. We shall have an infinite number of electrons in the negative energy states and indeed an infinite number per unit volume all over the world. But if their distribution is exactly uniform, we should expect them to be completely unobservable. So this was his argument, and this argument obviously had a challenge. This explanation became as what we call Dirac C, and it is needless to say that it was a controversial and he was target of serious criticism. In the opinion of Werner Heisenberg, it is quoted that the saddest chapter of the Werner Heisenberg quoted that the saddest part of the modern physics is and the remains of the Dirac theory. I regard it as the learned trash, which no one can take seriously. Here is a thing about the science. Ultimately, people's opinion do not matter. See, the criticism that Dirac has sustained, and it does not matter if the idea seems laughable. There is only one scientific authority, and that is nature. What matters is the idea that leads to testable prediction, and if those predictions can be verified. So this explanation was overpassed in the sense that a photon is absorbed, and that leads to electron and positron. And this was exactly what was verified in that Anderson's experiment. So I would like to end up my discussion with the quote of Weinberg: "The relativistic wave mechanics, in the sense of relativistic quantum theory of fixed number of particles, is an impossibility." So Dirac thought of the infinitely large number of electrons which are in the negative energy state. And later on, the subject has taken a leap and quantum electrodynamics was discussed. So on this point, I would like to conclude, and I would like to hand over to Ahluwalia sir, I guess.
Yes, I'm coming.
I'll stop sharing my screen.
Oh, right. So thank you very much for such a wonderful talk. I think it's a tough subject. Even the mathematics starts getting complex if one wants to really explain it fully. But you have tried in a very limited time to do justice to it. Thank you very much for that. And I think you almost did all the calculations also simultaneously in your presentation. That was just wonderful, and could make a very nice comparison between the non-relativistic and relativistic Dirac equation. So thank you. So Madhusudanji, if there are any questions, people can ask. You can raise your hand and ask questions.
If there are no questions, on behalf of all the participants, I thank Professor Anwane sir for his lecture on Dirac, Who Saw the Beauty in Mathematics. Thank you, Anwane sir, RC22. Thank you for your time and what you call expertise in dealing with this particular topic. Thank you.
Thank you, sir. Thank you, sir. I want to say only one line. I have developed a course on Udemy on this topic, and I will generate 100 free coupons. And before end of this meeting, I'll pass on those coupons link in the chat box for participants.
Thank you.
Thank you, sir. Thank you.
Thank you, sir.
Now, let us start the second session. The resource person for this session is the IAPT National President, Professor Ahluwalia sir. The title of the topic is Creating Designer Quantum States, Artificial Atoms and Their Lab Realization. Artificial atoms and their lab realization. So this is the topic to be dealt by Professor Ahluwalia sir. Before Ahluwalia sir starts, let me ask the young and enthusiastic undergraduate participant of this program, Priyamvada, to read the profile of IAPT National President, Professor Ahluwalia sir. Priyamvada, are you there?
Yes, sir.
Please go ahead.
Good evening, everyone. I've been honored to introduce our second speaker for the day, Professor P.K. Ahluwalia, sir. He's a professor in physics, a retired professor in physics from Himachal Pradesh University. He held many positions, including Professor of Physics, Coordinator UGC SAP Physics Department at HP University, Member Himachal Pradesh State Higher Education Council, Member Advisory Committee HP Private University Education Regulatory Commission, Member Advisory Committee HP Public Service Commission, Chairperson and Member Library Advisory Committee Himachal Pradesh University Shimla, Coordinator UGC Nodal Center of Computer Applications in Physics, Mathematics and Commerce. Currently, he is a consultant IQAC Bahra University, Dean Faculty of Physical Sciences from the year 2011 to 2013, Dean Planning and Teachers Matters from 2011 to 2014, Director, Internal Quality Assurance Cell from the year 2011 to 2014, Director, University Institute of Information Technology from the year 2000 to 2008, Coordinator, Nodal Center of Computer Applications from the year 1995 to 2005, the Chairperson of Department of Physics, HP University, Chairperson, Board of Studies in Physics, UG and PG, Member, Academic Council, Himachal Pradesh University, and he has been teaching since 1980. He has taught in St. Bede's College from the year 1980 to 1987. Since February 1987 in Department of Physics, Himachal Pradesh University. He retired in June 2015, and his research areas were condensed matter physics, dilute magnetic alloys, chemisorption, liquid meals and alloys, low-dimensional electronic gas, quantum dots, and computational material science. Physics educational research in epistemological study of the beliefs, attitudes, and expectations of physics learners, development of concept inventories in physics, and he guided 18 PhD students and guided 34 MPhil students. He has written 3 books on computational physics and related areas and edited 2 publications. His research and other faculties were a Nodal Center for Computer Applications, High Performance Computing Facility of 128 crores for electronic structure calculations using DFT, upgraded research and teaching facilities under FIST and UGC SAP. He introduced computational physics as a subject in UG and PG courses and organized a series of refresher course in collaboration with UGC HPU Academic Staff College. His publications in peer-reviewed journals and international conferences were more than 120 in high impact factor peer-reviewed journals, more in international journals. And his awards, he was awarded Commonwealth Academic Fellowship at the University of Edinburgh, UK in the year 1997-98. Best Teacher and Academic Administrator Award by HP University for the year 2012. Awarded Environment Leadership Award 2017 in individual capacity by Department of Science and Technology, Government of Himachal Pradesh, Shimla. He has visited abroad to countries United Kingdom, France, Switzerland, Turkey, and Thailand. Initiatives on the campus, he has initiated University Institute of Information Technology and remained its director from the year 2000 to 2008, implemented campus-wide optical fiber network in HPU campus. As part of FIST, established high performance computing laboratory for research in condensed matter research, did database design for the computerization of HPU examination wing as a live project with BTech IT students, and as a director of IQAC, he has implemented student charter, designed and implemented teachers evaluation performer, initiated biggest academic reform in the HP University through choice-based credit system under RUSA in 2013, implemented online examination for the RUSA at UG level, initiated SWOT on campus, university coordinator for RUSA, initiated creation and citation index for faculty members on Google Scholar and ResearchGate, achieved ranking for HP University to be among the top 25 universities of the country as per Nelson India Today survey. These efforts resulted in NAC grade A for the university in its 3rd cycle of accreditation and improvement of grade from 2.5 to 3.21 and jump for 2 steps from earlier B grade. As a dean, he has developed 12th 5-year proposal for funding by UGC, initiated proposal for having 50 kilowatts captive solar power project on HPU campus, initiated proposal for establishing community radio of HPU, prepared DPR for computerization of the university worth 3.69 crores granted by the HP government, prepared proposal of HPU for RUSA funding worth rupees 250 crores and initiated digitization for RUSA, digitization for HP University Library in advanced stage of implementation. He is also interested in science popularization, radio feature writing, development of spoken tutorials, community service editor, developed e-resources for statistical mechanics of the MSc courses for UGC, and sketching and also drawing. His membership of professional bodies he is a member of Indian Association of Physics Teachers currently, National President, IAPT from the year 2022 to 2024, member Indian Physics Association, IPA, currently on the executive, member Indian Science Congress Association, president of Himachal Physical Society, former General Secretary, Vigyan Bharati, and president of IAPT from 2022 to 2024. Seminars and conferences organized were 15 in various areas of physics, information technology, quality assurance, library science, and community service. Thank you.
Thank you, Priyamvada. Now the stage is yours, sir. Ahluwalia, please.
Thank you, Priyamvada. You really, I must thank you for all that. It could have been much briefer. So I think I must really start my lecture, and let me tell you that I'll try to. Yeah.
Sorry to interrupt, Professor Ahluwalia.
Yeah, please.
I think the introduction should have been a little longer to include your contributions to IAPT as the president. I think it is an outstanding contribution that you have made, and despite the time I'm taking to comment on it, I think I really want to add it to your introduction. Please carry on.
Thank you, sir, for your kind words. So I'll begin, and let me tell you the dilemma of giving this lecture. The dilemma is this, that number of times I was asked in the past 6 months, I was telling in the beginning also, that can we take these kinds of topics to the students in schools or not? Can we really talk to them about what quantum mechanics has done, the kind of progress which we are seeing around us in terms of technologies? And they have become commonplace now. So I thought, let me really peg my talk for an audience where school students, undergraduate students, or PG students, they can sit together and still appreciate what's the essence of that progress which we have seen because of quantum mechanics itself. And I begin this with an advertisement on top of this title slide, where there is an advertisement of Samsung selling smart TV using quantum LED technology. So that means this technology is already inside our homes. And maybe when we are watching our lectures here on the screens of our laptops or mobiles, etc., somewhere these kinds of things are being used. And then I also wanted that I should really talk about what people are very much thinking these days, whether it is in the newspapers or we start hearing about it in seminars, we are talking about quantum missions and all such things. So can we really go to that kind of a level where we can explain things and still make them appreciate the meaning of, say, a qubit? So this is the motivation of this particular lecture. And it has a number of elements in it which are very simple, but I think will be of interest to the students at that particular level itself. So this is a brief outline of the talk where I go from nanometers scale of nature right up to when Feynman was talking about a quantum mechanical computer itself. So I'll just try to go through that. So if we look at the scale of things around us in nature, I think man has really done a lot in tailoring many of those things which nature had made for us. So on one side, there is a list of things which are natural. On the other side, we have a list of things which are man-made. And we start seeing the scale at which we are operating right now. So if you look at the things which are natural, starting from dust mite to, say, the atoms of silicon, now, on the other side, we are seeing that we have been able to make things, say, starting from head of a pin, which is very small, of the order of 1 to 2 millimeter. And we are talking about carbon nanotubes, carbon buckyballs, graphene, etc., etc. And somewhere in the discussion of this, we find that quantum dots start appearing on the scene itself. So basically, when we are trying to talk about these quantum dots, we are making a transition from natural atoms to nano world to the artificial atoms. So if we think of the earliest kind of interaction of ours with quantum mechanics, at +2 level, we find Bohr's model is the one which is very often talked about. And I think even till date, what we find being taught at +2 level is right up to the Bohr's model. And then we start making some transitions towards, some electronic circuits, etc. And that's the end of the story in school. But Bohr was the one who really saw the implication of what he had suggested in his model of an atom. And a very famous quote of his is, anyone who is not shocked by quantum theory has not understood it. And one of the simplest conclusion which one comes across is the discrete energy states of the atom. And he talked just about the simplest atom in the periodic table, which was hydrogen atom. So if we really try to look at the things where we are today, I think we must go back in 1857 and try to see whether there was happening something also during that period or not. And what we will find is that this is a very interesting story till we reached the 21st century in quantum mechanics. And one of the very interesting things which was first of all reported was by, once again, Michael Faraday. And I think if Michael Faraday had been born in a period where Nobel Prizes were being given, he would have got not less than 4 Nobel Prizes for all the contributions which he made. He was the first one to look at how the interaction of light changes with gold when the size of the gold particles changes. And he published a paper in Philosophical Transitions of Royal Society in 1857. And he was basically a person whom you could see as a physicist or as a chemist, and a very multifaceted personality. So he took a salt of gold and he treated it with cadmium sulfide to get gold of nanoparticles. And what he saw was available, it is even now, a suspension which had not the golden color, but the color was the pink color. Now, these nanoparticles of gold and silver were used quite a bit by the architects and the designers of the churches in creating colored glass panes. And I think if we go anywhere around in churches, we will always find that the churches have beautiful panels showing beautiful stories from Bible. And this was a result of the understanding of the fact that if the size of the particles become smaller, and if we make use of various sizes of the particles, we will find that the light will interact with those particles in a very, very different fashion. Now we come back to 21st century. And in 2023, this kind of a discovery was celebrated by giving Nobel Prize to 3 people, Mungi Bafendi, Louis Bourg, and Alexei Yakimov. And in fact, what they achieved in their experiments actually echoed what Faraday did in 1857. And they were able to do that in 1980. And the work was initiated by the Russian physicist Alexei Yakimov. And I think this is the most interesting part of the story itself. And this Russian physicist was a solid-state physicist who made significant contributions to the discovery of the quantum dots. And this is how he arrived at this groundbreaking material, which can be created in the lab itself, as Faraday must have done. He did by a chemical route, whereas Yakimov was trying to do that through the physical route. So it was in late 1970s and early 1980s that Yakimov conducted his experiments at Vavilov State Optical Institute in Leningrad. And his goal was to explore the behavior of nanocrystals, that is tiny particles, embedded in a glass matrix. And for that, he picked up the nanocrystals of copper chloride. So he initially worked with copper chloride nanocrystals only, and he synthesized those within a molten glass matrix. And when these were exposed to light, they exhibited fluorescence and emitted different colors. And he was able to arrive at a very simple conclusion that the variation is in color is because of the size of these nanoparticles. Smaller the nanoparticles were produced, we were finding that we were on the one side of the visible spectrum. The particles were blue in color, and as we moved with bigger and bigger sizes, the color changed. So this was a very interesting size-dependent behavior, which really intrigued him. In his Nobel lecture, Yakimov only uses these 2 slides to explain how he was able to synthesize these kinds of particles in oversaturated solid solutions. And he was able to explain how the optical properties actually varied with the size. Now, if we try to look at the simple explanation of this, and if you see the cartoon on the right side of the screen itself, you will find that when, say, blue light is thrown on these nanoparticles, which maybe we can call as quantum dots, the interaction leads to different colors. And we can see the fluorescence of that as a result of the emission of light after interaction itself. So he was very clear about one thing, that these results are basically the quantum phenomena. And it is the confinement potential which is actually leading to these kinds of behaviors which were being observed. And he also was able to underline the fact that smaller the nanocrystal, the more pronounced this quantum confinement effect was. And he was trying to think of these as some kind of a replication of some kind of a quantum harmonic oscillator model. Now, it was in 1981 that he wrote another paper and reported the quantum size effect in copper chloride nanocrystals. And that is where typically the word quantum dot was actually made use of, which revealed the size of nanocrystals' influence on the optical properties. And that these quantum dots exhibited discrete energy states due to the confinement itself. So now if we look at these quantum dots, we can always see that these are confined regions in which we can imagine how the electron waves with different wavelengths are getting generated. This is a kind of a cartoon which I have taken from the Nobel Prize website itself, and it very nicely explains what is actually happening as the particle size shrinks. And to further understand it, he worked with his brother, who was also a theoretical solid-state physicist, to suggest that what kind of model we can use for explaining it. And then they relied very easily on one of the earliest models of solid-state physics to explain the phenomena which happen in crystals itself, that is choosing, say, a periodic scale well potential and talking about the discretized energy in that kind of a situation. So when we are actually talking about these kinds of electrons confined in spaces, they remind us of that are they not like atoms only, which we find in nature? The answer is that there is a difference, and that is why we call these as artificial atoms. One is that they do not exist naturally and they are man-made. They are not part of the periodic table. And the key to their fabrication is confining or trapping electrons or holes in solid-state crystals in so-called quantum materials, which are a very hot area these days. This requires a confining potential, which is not an electrostatic potential, which we see in the Bohr model, and is the backbone of what we try to see in the hydrogen atom itself. So whole of the periodic table basically has in its foundation the electrostatic potential, which is doing the trick. So we need to really look for a model typically other than involving electrostatic potential, but is effective to confine an electron or a hole. So can I really think of explaining this to the students? And I think the simplest thing which we can think of doing this is that maybe we can try to set up a Schrodinger equation, try to solve it, and then try to see whether this idea of confinement leads to the quantization of energy levels or not for a typical potential, which is other than the Coulombic potential. And the best part of this is that maybe when we think of a typical potential, which is, say, a kind of a particle in a box, we can analytically solve that also and explain it. But maybe when we are in school, we don't really try to do that. So can we really still talk about this kind of a confinement and convince our students that yes, this is how we can model an artificial atom, and we can see all those characteristics which we see in a typical Bohr model of an atom for the hydrogen itself. So the simplest model which we can think of is a quantum box confined in a trap as a trapped particle in all directions. Outside the box, potential is infinite in all the directions, and inside it, it is zero. So am I going to set up Schrodinger equation? Answer is no. Though I am just, for the purpose of completeness, writing the three-dimensional Schrodinger equation for this kind of a problem on the screen. Here, I would like to underline that we are using m star as an effective mass, which actually takes care of not only the Coulombic potential which is there, but other kinds of interactions which may be there inside the crystal itself. And we can always see, and that is what physicists are very clever in doing, we can see this as nothing but not one three-dimensional Schrodinger equation, but three one-dimensional Schrodinger equations corresponding to each of the axes. But then I said, I am not going to solve this, though it could have been possible to solve it even at +2 level. But the moment this differential equation appears, I think we can just put the people off. So can I make use of dimensional analysis to put my point forward to the students to appreciate what is happening? So what one can really appreciate is this, that energy of that confined particle definitely is going to depend upon the mass of the particle. Other is the size to which this particle has been confined. And then I bring quantum mechanics in terms of the Planck's constant. So I say that energy corresponding to the confinement in x direction depends upon these three variables. And maybe this problem is tractable by dimensional analysis itself. So you can very easily see on the screen that the principle of dimensional homogeneity can be applied to see that what will be the power of m, what will be the power of Lx, and what will be the power of h bar, telling us the kind of dependence which this energy will have on these three variables. And what we find is that the value of A turns out to be -1, the value of B is nothing but -2, the value of C is equal to 2. So what is this Ex equal to? If I just keep myself to this fact that this Kx is nothing but a kind of a constant, I can very easily see that the rest of the part which is written for the energy is nothing but what we will get by solving these differential equations also. And if I now bring in all the three dimensions, the total energy of the system can be written very easily in the form of this formula. And then I also, put by hand to bring in the discreteness of the energies, this nx square by 2 factor. And I can even now talk about that, okay, when we are talking about this energy which depends upon three spatial directions, the wave function, which is the solution of the Schrodinger equation, basically is telling us that this energy corresponds to a state described by the three quantum numbers nx, ny, and nz, where nx, ny, and nz take on values from 0, 1, 2, and 3, and so on. So I think the moment I look at this formula itself, I can see that the energy Ex depends upon the size of confinement itself. Secondly, the behavior is that of an artificial atom, and the energies are discrete in nature. So I think if we look at the level at which we are targeting the presentation, this can be a reasonably good, plausible argument to be given to the students to appreciate the idea of the quantum dot itself. So after this, we can also talk about what are the differences between the real atoms and the artificial atoms and elaborate on those. So first, we can talk about origin and composition. So naturally, I talked about this also. Real atoms occur naturally and are the fundamental building blocks of matter. They consist of a nucleus, protons and neutrons surrounded by electrons, whereas artificial atoms are engineered structures created in the laboratories. They do not occur naturally and are typically composed of different materials, for example, quantum dots, superconducting circuits, or trapped ions. Whenever you are going to any talk on quantum computing, you are always hearing about these quantum dots, the trapped ions, etc., etc. And I think this is how this idea can be conveyed to the students. Size and scale. Real atoms are extremely small, with typical sizes on the order of angstroms, that is 10⁻⁻10 meters, whereas artificial atoms can be larger and more controllable in size. Researchers can tailor their dimension to achieve specific properties. And that is why they are becoming a commonplace in the electronic, say, items which we see around us. Energy levels. Real atoms have quantized energy levels due to electron orbits around the nucleus. I think this is a very simplistic way of telling, whereas maybe we need to abandon later when we go to higher studies the idea of the electron orbit itself. Artificial atoms also exhibit quantized energy levels, but these levels can be engineered by adjusting the confinement potential. For example, changing the size and shape of a quantum dot itself. Interaction strength. Interactions between real atoms are governed by electromagnetic forces, whereas interactions in artificial atoms can be tuned by design. For example, superconducting qubits can have strong coupling to microwave photons. Applications, I think real atoms are essential for chemistry, biology, and the natural world, whereas artificial atoms are primarily used in quantum technologies such as quantum computing, quantum communication, and quantum sensing. I think it is also essential to emphasize what is the similarity between real atoms and artificial atoms. So quantization of energy is one. Behavior of mechanics governing behavior is another. Both real and artificial atoms follow the principles of quantum mechanics. Their behavior is described by wave functions, probabilities, and quantum states. Wave particle duality is inherently there in both the cases. Role in quantum information processing also brings in the use of both real atoms and artificial atoms. For example, real atoms are used in atomic clocks and quantum sensors, while artificial atoms serve as qubits in quantum computers. Manipulation and control. Definitely, I think we have all the means to control the real atoms as well as the artificial atoms. Now, one thing which emerges out of this is the idea of the state which can be brought before the students as a kind of representation of the state of the quantum dot itself. And on the screen, you can very easily see that a wave function can be introduced. We can talk about the probability. We can also talk about a symbolic representation of the meaning of a quantum state itself, which can be described in terms of these four quantum numbers. Now, there is one thing which is very necessary when we are talking about of ideas that yes, we can produce these kinds of artificial atoms. But at the scale at which we are using these now, I think the mass production of these kinds of possibilities is again a very challenging thing. And what in the team of the three Nobel laureates, Mungi Bawendi did was that he gave us a chemical process in which quantum dots can be produced on mass scale. And the idea was actually very, very different, very, very simple. You know that even in high school, when we tell our students that, okay, let us try to generate crystals of copper sulfate, we always try to say, okay, what we can do is we can put a kind of a nucleus, which is a small crystal of the copper sulfate itself, to create more crystals in the solution. And this is precisely what he did. And what he did was he created a device which is typically a kind of a round-bottomed flask with three openings in it, in which there was one instrument to measure the temperature. Other was a kind of a syringe by which you can inject that material whose quantum dots you wanted to produce. So the moment this solution of, say, cadmium sulfide gets injected into this solvent, what we find that the crystals emerge. But these crystals don't grow. Rather, what happens is they stop growing, because when this material gets injected, the temperature falls, and that really stops the process itself. So what Vivendi did was, he said, let me really heat the flask and see what is happening. And what he found was very interesting, that the crystals started growing again. And I think this was the beginning of the generation of these artificial atoms, or what we call as quantum dots, on the mass scale. And that is why he was also given a Nobel Prize. Now, the signatures of these quantum dots you will find are available otherwise also in some other situations, like in the formation of, for example, a buckyball, which is again a kind of a realization of such an artificial device, which is also a kind of a possibility of confining the electrons. There are some other ways and means also by which we can confine the electrons and produce, say, the quantum dots, and not only just quantum dots, but we can create arrays of quantum dots on a substrate itself. Now, the key properties of these quantum dots, as I have just said, I would like to once again emphasize, are zero-dimensional confinement, bound quantized energy state. They have a well-defined band structure when we try to bring them together, and atom-like electron wave functions. Now, these quantum dots are around us in almost numerous practical applications. Light-emitting diodes and displays, which have changed the way we are using and having efficient ways of using energy, have changed the world. Light-emitting diodes are the ones which have been enhanced a lot by the quantum dots for providing tunable and efficient photoluminescence in displays, QD-based screens. They offer vibrant colors and improved energy efficiency. So our monitors and televisions are an example of that. They have brought a drastic change in the harnessing of solar energy and in creation of solar cells using photovoltaics. And they enhance light absorption, and energy conversion efficiency also gets increased. In biomedical imaging and sensing also, they are making a lot of difference. They serve as fluorescent probes for cellular imaging, drug delivery, and disease diagnosis. So we are finding that now they are everywhere. And this has been the case with physics all the time, that physics has indeed impacted the health sector, the imaging, the diagnostics, etc., in a very, very big way. And I think the quantum dots are also coming forward and filling that kind of a thing. Photoconductors and photodetectors, catalysis applications. We always talk of that we use, say, finely divided nickel as a catalyst, and we always tend to increase nothing but the surface area for the catalyst to act efficiently. And I think quantum dots are naturally tolerable such materials which can be used for those processes. Quantum-based cryptography and spintronics. So the moment we start talking about it, I think we start talking about the latest things which are happening around us in terms of quantum technologies, which are the buzzwords these days. And we are hearing a lot these days that these can be used for secure communication, for quantum computing, and maybe quantum dot-based quantum key distribution systems. So let us try to see, again, for the purpose of highlighting the differences, that what is the difference between quantum dot when we try to look at it from the point of view of classical mechanics and their role in building quantum computers. I think this is a very important point where we need to really talk about this also. So when I'm saying classical mechanics, I'm basically talking about classical computers, and then how you can compare their behavior with quantum computers. We know that classical mechanics, it means that classical systems follow deterministic laws and behave predictably. Their properties are continuous and well-defined, whereas quantum dots are nanoscale structures where quantum mechanics dominates. Their behavior is inherently probabilistic due to wave-like properties of electrons. Quantum dots can trap single electrons and exhibit quantized energy levels. When I say this, I don't mean that the computers which we use, which are not typically classified as quantum computers, they use a lot of quantum technologies in the making of those machines itself. Quantization in classical mechanics, energy levels are continuous. For example, an electron in a wire can have any energy. Whereas in quantum dots confine electrons to specific energy levels, and these discrete energy states allow precise control over individual electrons, making them ideal for quantum computations. So if I have to really talk about a typical example of how we are making use of these quantum dots with a single electron for the new technologies, I think that can also be made understood very conveniently to the students. And we can always make use of these representations to highlight how we really make use of these symbols for representing the things which we are talking about. So if I have two different states, one with up spin or down spin, or what we can call as psi1 or psi2, or in the Dirac's notation as a 0 state and a 1 state, we find that quantum mechanics says that you can superpose these two states to get a new state, and the weights A and B can really decide that this is not just one state, but it is a very large number of states which become available to us just by means of superposition of these states itself. So we can definitely talk about that what is the meaning of a qubit different from a bit. And I think that is also an essence at that particular level itself. And then we can introduce the vocabulary also at that particular level. When we are talking about qubits, classically speaking, they represent information as either 0 or 1. Whereas when we are talking of quantum dots, they serve as quantum bits, and each quantum dot can hold a single electron. Its spin can be up or down, and it can have superposition of states which can enable those kinds of computations or the fascinations which we are talking in the context of quantum computers. Classical systems do not exhibit entanglement, whereas the quantum dots can also become entangled with other qubits. And this entanglement allows for non-local correlations and enables powerful quantum algorithms. Another thing which is there is the concept of decoherence. So classical systems are robust against environmental disturbances, so they don't get decoherented. Whereas in the case of quantum dots, they are very sensitive to their surroundings. And this decoherence, that is interaction with the environment, limits quantum coherence. And I think this is something which is a kind of a area in which people want to control this decoherence itself of the stable qubits. Then you can also, using these qubits, create gate operations. In classical mechanics, we were talking about and, or, not, etc. In the case of when we try to create those kinds of logical electronic gates, we can also create quantum gates when we can manipulate qubits by changing, say, for example, the tunnel barrier between neighboring quantum dots, and we can have controlled interactions. In the case of applications, we know that classical computers excel at everyday tasks like calculations, simulations, and data processing. Quantum dots hold promise for quantum computing, and I think this promise is going to get converted very soon into reality. Quantum computers are already in place. People are trying to increase the number of qubits which they can use in the quantum computers, and that number is also increasing. We are very much excited that how they are going to influence cryptography and how simulating the quantum systems for the purpose. And this race for quantum computers is on. You talk of any big IT company, they are into it. Google is there, IBM is there, Microsoft is there, Amazon is there, Oracle is there, Intel is there, and they are, having a race. Cisco is there, Apple, SAP, Dell. You will find all these companies are having a kind of a competition with each other to overtake the other companies. So quantum dots hold immense promise for quantum computing, but practical implementations are still in progress. And I think in the last 2-3 years, we have moved ahead a lot. Researchers continue to work on overcoming challenges related to quantum coherence, scalability, and error correction. When a company successfully develops a quantum dot based quantum computer, I think it will mark a significant milestone in the field of quantum information processing itself. But I think whenever we talk of quantum dots or quantum computers, I think we cannot forget Feynman in that context. Because he was the one who, first of all, started talking about that there is lot at the bottom. And in his very famous book, which he actually delivered as a set of lectures and was actually published after his death, there he said that this study of quantum mechanical computers, if we are talking about that, is embedded in our aim to exhibit some Hamiltonian for a system which could serve as a computer. I think this is a typical statement which only a physicist can use and not a computer scientist. In the preface of that book, even Feynman says that computer scientists are not like the physicists or physics walas, because when they talk of computer science, their science has nothing to do with the natural world as it is. And he also pointed out that at any rate, it seems that the laws of physics present no barrier to reducing the size of computers until bits are the size of the atoms and quantum behavior holds dominant. I think these are prophetic words, and I try to see the lectures which were compiled were in 1996. Just after almost 30 years, what he has been saying is turning out to be true. But then I think we must take another message with us today, because we are talking about Feynman in the end. He made a very interesting quotation, which is of, I think, a lot of interest to the young students who are sitting in this particular webinar also. He said, fall in love with some activity and do it. Nobody ever figures out what life is all about, and it doesn't matter. Explore the world. Nearly everything is really interesting if you go into it deeply enough. I think it's a very interesting statement. Nearly everything is really interesting if you go into it deeply enough. Work as hard and as much as you want to on the things you like to do the best. Don't think about what you want to be, but what you want to do. Keep up some kind of a minimum with other things so that society doesn't stop you from doing anything at all. I think the last statement is a very interesting caution which he gives to the dedicated persons, that look, you also need to be a bit worldly so that you are able to concentrate on what you really want to do. So I think with this quotation, I would like to end. And these are the references which I have made use of and the websites which I have used for preparing this presentation. And as I told in the very beginning also, the challenge was, can I take this idea of quantum dots and quantum bits to the high school students and maybe the undergraduate students also. So thank you for being with me in the lecture. And I'm sure that these quantum dot arrays are going to be everywhere in the next few years. Thank you very much.
Thank you, sir. We look forward to Professor Deshmukh, sir, for his expert comments on this topic, on this presentation.
Well, not expert comments, but as someone in the audience, I think this was a fantastic talk, Professor Ahluwalia ji. This is amazing, very a topic of great importance, not just for today, but for tomorrow and for the future of science and technology. What a beautiful coverage you provided. Means doing the analysis in very simple terms, using dimensional analysis, and showing how these quantum dots can be controlled, and the technologies that can emerge out of it, which have already emerged out of it, and even more so coming in the very near future. So the kind of control we have on manipulating quantum, energy structures, and what we can do with such systems. So these are artificial in some sense. Nature doesn't give them to us, but this is a tremendous way of going forward by generating, by creating, manipulating properties however we desire them. This is marvelous. I think it was a great talk. I'm sure this talk is recorded, and I'm sure it must be viewed by those who missed it. And I'm sure that those of us who had the opportunity to be with you this evening, we will like to go through it again, because it had huge amount of insight in quantum properties that you can manipulate. So I think there is much to learn from it, and even those of us who have been with you in this talk will like to see the recording again to extract the full impact of what you covered. Beautiful talk. Thank you very much.
Thank you very much.
Thank you, sir. Okay, Professor Bhupati, sir, please go ahead. Unmute yourself.
Thank you. I must appreciate the wonderful talk by Professor Ahluwalia. It's very nice to see that initially I was talking about something for the UG level, something for the students. He has really surpassed that expectation. Thank you very much, Professor Ahluwalia. I'm really very pleased. I'd like to share one observation, that while Professor Ahluwalia was talking about the contribution of the three scientists regarding those development of quantum dots and those particles, how they did it, I was wondering that these people must be from chemistry. And finally, I could find in reference that, well, they were awarded Nobel Prize for chemistry. So that way, in a way, goes to show that how chemists apparently, well, we normally tend to think, particularly being the students of physics, we normally tend to think, well, there's nothing the chemist can do in this particular field and that sort of thing. But well, he has wonderfully broken that idea. And finally, I could realize that, well, these three gentlemen, these three Nobel laureates were chemistry Nobel laureates, and that approach, that tenacity to that sort of experiment, it is really, really wonderful. And as we know, there are a good number of people from chemistry has contributed in very tenacious experiments in physics in a big way. And these three scientists are also of that category. So I once again like to thank Professor Ahluwalia for this wonderful talk. Thank you. Thank you very much.
I agree. Wonderful talk. And it summed up so nicely in that Feynman quotation, that Feynman also said everything in his lectures. And the last quotation, I want to, when the YouTube link comes, I would like to have it pasted on my thing. the advice for students. That was wonderful.
Yes,
And
yeah,
then
that is
how
true.
you do dimensional analysis to work out the energy. That's also very, very beautiful. Thank you, Professor Ahluwalia, for a very beautiful talk.
Thank you, sir. Any other comments or queries from the participants? Dr. Sandeep, sir, yesterday you wanted to say something at the end.
Good evening, sir.
Well, you're audible, sir. Please go ahead.
Sir, very interesting, sir, जो है sessions last 2 days. I am very happy, sir. I am from a degree college. सर सबसे बड़ी अच्छी बात ये है कि मैं भी जो है फर्स्ट टाइम जो है IAPT का जो NGP एग्जाम होता है अपनी यहाँ मैंने कराया जो है, और बच्चों ने बहुत ही चढ़ बढ़ के हिस्सा लिया उसमें सर है, और बहुत खुशी हुई। लेकिन सर फिजिक्स में जो है बच्चों के प्रति जो इंटरेस्ट है बहुत तेजी से घट रहा है सर। तो कुछ सुझाव मैं चाहूँगा सर आप लोगों से कि मैं क्या करूँ ऐसा कि जो है बच्चे फिजिक्स के प्रति इंटरेस्ट लें। खास तौर से लैब में जाना पसंद ही नहीं करते हैं बच्चे सर। तो सर आपका थोड़ा कमेंट चाहूँगा इस पे आप लोगों का सर कि मैं क्या प्रयास करूँ कि जिससे बच्चे जो है लैब में जाना पसंद करें और प्रैक्टिकल जो है करना चाहें सर।
एक्चुअली देखिए, ये जो टॉक थी इसका बेसिक पर्पस भी यही था कि जो ये हमारे सब्जेक्ट्स हैं फिजिक्स, केमिस्ट्री, स्टेम एजुकेशन जो है ये बहुत इंटरेस्टिंग है। शायद हमको उनको सरस बनाना पड़ेगा, उनकी नीरसता खत्म करने की ज़रूरत है। थोड़ी थोड़ी अच्छी स्टोरीज की बात करने की ज़रूरत भी है, और मुझे लगता है फिजिक्स में इन चीज़ों की कमी बिल्कुल नहीं है। बहुत कुछ है जो हम कर सकते हैं इन स्टोरीज के माध्यम से। और हमारे अरविंद कुलकर्णी जी यहाँ पे हैं। आपने बहुत क्वांटम कंप्यूटिंग वगैरह के बारे में स्कूल्स में जाकर के काम करने की कोशिश की है। हमारी बहुत लंबी लंबी चर्चाएं भी होती रही हैं। And we always felt that some or the other we must go, this is our duty also, and talk to our students in a tone and tenor in which they understand. We must really not bring them up to our level, but we need to go to their level so that they can appreciate the things. I think that is the essence of everything. And I believe that ups and downs आते रहते हैं. ये ऐसा नहीं है that this is going to remain always like that. We are in a transitory phase also because of national education policy. People are not understanding what is the meaning of major and minor subjects and how they can help them, except in engineering institutions. Otherwise, you will find that there are a number of things, number of possibilities which we can do very carefully. I would like to tell you one thing. ये जो इस किताब की मैंने बात की, फाइनमैन की किताब की, ये किताब आप ना फाइनमैन के लेक्चर से भी बेटर पाएंगे इनको जब वो ग्राउंड पे आने की कोशिश करता है। I mean, it is amazing the way he brings things down and explains them with minimum of mathematics. Minimum of mathematics. I mean, it's just great. He explains computer क्या होता है. He explains Turing machine क्या होती है. He explains quantum logic gates क्या है, कैसे वो काम करते हैं. उसके बाद वो क्वांटम मैकेनिकल कंप्यूटर को थर्मोडायनेमिक्स की सेंस में एक्सप्लेन करने की कोशिश करता है, और उन फिजिसिस्ट के जिन्हें कि आज हम नाम सुन रहे हैं ना, बेनेट है और उस किस्म के लोग, उनके वो पेपर्स को कोट करते हैं उस किताब में। आई थिंक इट इज़ वेरी नेसेसरी कि हम बच्चों को ना ये अच्छा साहित्य जो है साइंस का उन तक पहुंचाएं, और हम अपने अपने क्षेत्र में भी ये कर सकते हैं। आप फाइनमैन की किताब का प्रीफेस ले लीजिए, बच्चों को उसकी हिंदी में ट्रांसलेशन करके हाथ में दे दीजिए कि देखो पढ़ो। आप सीवी रमन का कुछ उठा लीजिए, उनको हिंदी में ट्रांसलेट करके या मराठी में ट्रांसलेट करके आप उनको दे दीजिए। यू विल सी द इम्पैक्ट। हमको, मेरा मानना ये है, IAPT का जो फोरम है ये इतना बढ़िया फोरम है, वास्ट है, ऑटोनमस जैसा सिस्टम है ये, इसमें कोई किसी को रोकता नहीं है कुछ करने से। कुछ भी आप खड़े हो जाइए, कहीं भी जाके आप कुछ करना चाहते हैं कर सकते हैं। अब ये देखिए, ये प्रोग्राम भी जो आप देख रहे हैं, ये हमारे रीजनल काउंसिल वाले लोग कर रहे हैं। पहले हमने गुजरात में किया, फिर हमने इसे केरला में किया, अब हम तेलंगाना वालों के साथ मिलकर कर रहे हैं। तो मेरे को लगता है हमको दृढ़ प्रतिज्ञ होना पड़ेगा इन चीज़ों को आगे बढ़ाने के लिए। अगर हम हो पाएंगे तो बड़ी अच्छी बात है। एक हाथ खड़ा हुआ था बीच में, रावत रुतिका, यू रेज्ड योर हैंड, वुड यू लाइक टू आस्क योर क्वेश्चन नाउ?
Yes, sir. Sir, my question. Hello, may I ask,
Yeah.
sir?
Yeah, please.
Yes.
Sir, my question is, recently the Italian scientists have frozen the light in a in a crystalline solid. So, sir, what is this? Is this thing that you have discussed is related to that milestone?
नहीं, मेरे को तो नहीं लगता है, मुझे उसके बारे में ज़्यादा अंदाज भी नहीं है, आई मस्ट एडमिट दैट। बट हाँ, एक बात ज़रूर है कि शायद वो जो फ्रोजन हुआ है वो क्रिस्टल के अंदर ही हुआ है। तो इसका मतलब है दैट समवेयर the interaction of light with crystals is having another dimension when that result has been reported. I think maybe we need to go deeper into it and appreciate and understand that. मैं भी आप ही की तरह उसके बारे में उत्साहित हूँ, जागरूक हूँ कि हाँ, ये हो क्या रहा है। हमने ये क्या कहना शुरू कर दिया कि लाइट को हमने रोक दिया, इसका मतलब क्या, हमने फोटोन्स को रोक दिया, बट फोटोन्स का तो रेस्ट मास होता ही कुछ नहीं है। तो ये क्या हो रहा है, ये सवाल दिमाग में आने लगते हैं। तो हम कैसे करें
Yes.
इसको? How should we really understand that? So Rutika ji, the way you are very much excited about it, and that's good. I'm great that you are keeping an eye on all these things. We are also excited about it, and that is also, I think, one of the very important things in studying sciences, that it excites you to look at phenomena around you. So I
Thank you,
hope,
sir.
इससे ज़्यादा तो मैं क्या बोलूं?
Yeah, sir, I have one more question. I think I missed it in your presentation. You talked about that nature of the potential is not electrostatic for artificial atoms. So then
Yes.
what would be its nature?
देखिए, what I did was, in my lecture, I was saying that you have to confine something, right? And then I defined that by saying that there is a region in which potential is zero, and around that, potential is so big that particle cannot really go out in any way for the time being, right? So once I have done that, if I have talked about it, then we define potential, that V is equal to zero within that box, and outside that, it is infinity. तो जब आपने अगर श्रोडिंगर इक्वेशन जो मैंने लिखी थी उनको ध्यान से देखा होगा, तो हम ये मॉडर्न फिजिक्स में भी इस्तेमाल करते हैं। जब मॉडर्न फिजिक्स के नाम से हमको क्वांटम मैकेनिक्स पढ़ाई जाती है अंडर ग्रेजुएट में, कि हमको श्रोडिंगर इक्वेशन सॉल्व करनी है, द बेस्ट इज लेट अस ट्राई टू सॉल्व वन डायमेंशनल बॉक्स एंड देखें, और उसका सॉल्यूशन बड़े आराम से ना, आपको सॉल्व करने की भी जरूरत नहीं है, यू कैन इंट्यूटिवली सी कि उसका सॉल्यूशन क्या आने वाला है। पोटेंशियल जीरो है, एक तरफ डबल डेरिव बैठा हुआ है, दूसरी साई का, दूसरी तरफ भी साई बैठा हुआ है, तो वो क्या साई हो सकता है, उस सेकेंड ऑर्डर डेरिवेटिव लें तो आंसर साई आ जाए, एंड सडनली वी सी साइन फंक्शन कैन बी वन, बिकॉज आप उसका डबल डेरिवेटिव लोगे तो आपके साथ साइन भी आएगा एक माइनस का, और मे बी यू कैन
Right.
थिंक ऑफ चूजिंग कॉस। तो आप बिना सॉल्यूशन किए भी इन चीज़ों को ना गेस कर सकते हैं। एंड आई थिंक कई बार, आई थिंक जब साइंटिस्ट बहुत कुछ सोचने लगते हैं तो वो ना ऐसे ट्रिक्स इस्तेमाल करते हैं चीज़ों को करने के, जैसे डायमेंशनल एनालिसिस इज ए वेरी इंपॉर्टेंट ट्रिक इन द हैंड्स ऑफ ए साइंटिस्ट टू अंडरस्टैंड समथिंग, टू इनिशियली गेस समथिंग एंड देन वर्क आउट द डिटेल्स। ये फाइनमैन जैसे लोग इसमें माहिर लोग थे। I
Okay,
hope.
sir. Thank you. Yeah. Thank you, sir.
Susan ji, I think लोग 9 ही बज रहे हैं। I can, yeah, please. Yeah, yeah, please.
Sir, good evening, sir.
Good evening.
Sir, I am Hamsadar Rajbakshi from Assam.
Yes.
Sir, I want to know, ask one question to Ahluwalia, sir. Hello?
Yes,
Please,
sir.
please.
You can ask. You can ask. Please.
Sir,
Ahluwalia sir is ready to answer.
Sir, nowadays people are studying or speaking about position-dependent mass Schrodinger equation. Sir, what is your comment in this regard?
Please repeat your question again.
Position-dependent mass Schrodinger equation. People are studying about this
Position-dependent.
mass Schrodinger equation.
Is it position dependent bus Schrodinger equation?
Yes, sir.
Bus Schrodinger equation. I don't know. I have heard about Schrodinger's cat, etc. But where this is coming, maybe if somebody else can comment on it, I will be very happy. मुझे अंदाज नहीं है position, bus and Schrodinger equation.
That means the effective mass is taken in the Schrodinger equation.
You are talking about effective mass?
Yes, sir.
Yeah.
Okay. All right.
I'm sure it is about
There's
effective
three
mass.
ambiguity parameters are there.
See, once again, when we talk about this effective mass, it is also a kind of an approximation which we bring into the system. For example, we say that when I am talking about an electron, it's not just moving as an independent particle. It is not like a free electron gas. First thing is that we are saying in a crystal, it is moving in a periodic potential. But then somebody says, look, it is not just that. Even these electrons can interact with each other and influence each other. And how that gets reflected. So we find that in solid state physics, we talk about this in terms of E versus energy versus wave vector relationship. And we find that the effective mass is defined as nothing but the reciprocal of the second order derivative of the E with respect to K. And for example, this E for a free electron gas is nothing but h bar square K square by 2m itself. So you can take the second order derivative of this and you will find it will turn out to be a kind of a constant, because K square's derivative, if you take twice, it will turn out to be some number. So basically, when we are bringing this, we are saying that this relation is not necessarily a parabolic relationship. It can be different from that also, which you can see in any typical solid state physics book also, that how even with dimensionality, E versus K relation changes. I hope I have tried to explain this idea of effective mass. Maybe it will help you to understand that.
Okay, so thank you, sir. Thank you for that.
Thank you, sir. It is already 9. And let me remind few things, sir. Professor Anwane, sir, posted a link to get his pass for viewing the Udemy content he developed. And he posted on the chat box. Any of you, if you want to view that, view that content, can copy the link. It is posted on the chat box. It is there. You can copy it and save. That is one thing. If no more questions are there, let us try to wind this. First of all, let me thank all the Central IAPT leaders for supporting us in organizing this program. Professor Ahluwalia sir, our secretary ma'am, and all the senior members. I also thank all the speakers, starting from Mrutyunjay, Dr. Mrutyunjay, and the very enthusiastic Ajay Ghatak sir, Professor Prutul Desai sir, Professor P.C. Deshmukh sir, Professor Anwane sir, and Ahluwalia sir again for giving us valuable time and helping us conducting this program to reach the participants in a successful manner. And few of the participants are asking e-certificates for attending this program. Definitely, we have your contact number or mail IDs. We'll share e-certificates to you after 2 to 3 days. And all of you are asking for the recording of this event. Yes, we have recorded all the sessions. We'll just edit them and convert them and post them on YouTube and share the links in IAPT group so that you can view all the 6 lessons on YouTube. And our national president also promised to make them in short videos. We'll try to do that also. And
Yes.
sir,
May I just make one comment?
yes, sir,
That I
please.
would
Yes,
like
sir.
to have your attention, what I am going to read now. And Professor V.C. Deshmukh, I would like to have your attention. There was one message which I got as a result of this set of lectures. And sir, I would like to read it. It was indeed a pleasure the way Professor Ghatak gave his responses in the interview. And your invitation to him to venture in memory lane with audience was just great. I enjoyed his candid recollection of time spent in Jaipur with Professor Loknathan. Beside, you very aptly put my mind out in your question about introducing quantum mechanics at school level, and his answer about revamping school syllabus and teachers training in modern concepts and problem solving. I enjoyed full time this presentation and interview. I have received many such feedbacks for this set of lectures, and I can only say, sir, IAPT has nothing else to give you but express their deep gratitude. Professor P.C. Deshmukh, Professor Ghatak, Professor Pruthul Desai, Professor Mrityunjay, Professor Anwane, and my hats off to Dr. Madhusudan, that who arranged this wonderful set of lectures. Professor Anwane did a very difficult job today. I must say that, because that is not an easy topic to really talk about. But I think we touched upon Dirac, who always used to understand mathematics, and he always wondered that why people use so many words to explain the things when there is mathematics before us. So I think that is just great, and I'm hopeful that you will enjoy this series in future months also, and maybe we will try to give attention to what Professor Ghatak today said, that instead of doing it on 3 consecutive days, we can split it on 3 separate days also. So thank you very much, Dr. Madhusudan. Sorry for stopping you.
No, thank you, sir, for your.
Thank you all. Thank you,
Heartiest
Madhusudan.
congratulations. Heartiest congratulations to Telangana RC. You've done a great job.
Yeah.
Thank you. We are also show our gratitude. We can't give you anything, but the support you have given is tremendous, sir, for organizing this program, sir.
I think
wonderful job done, Dr. Madhusudan. Thank you.
Thank you, sir. Thank you, sir.
Good night.
Thank you and good night.
Thank you. At the end, I thank all the RC22 members for supporting me. Thank you all the participants for your active participation. Now, I declare this session ends here, and I will be sharing the e-certificates, and I will be also sharing the YouTube videos of this program soon. Thank you one and all for your active participation. Thank you, sir.